Hi, everybody. Welcome. It's great to have you here with us on what is, despite my backdrop, actually quite a grey, cloudy November day here in London. I hope the weather is a bit kinder wherever you are. It's been a little while since we've had an IBIPSA education webinar, so I'm delighted to be back with a new series. And this series is going to be spread out over the next several months. We'll probably have webinars approximately every 3 months or so. So this first webinar in the BOPTEST series is entitled From Parameter Optimization to Emulator Development for Improved Building Control Modeling with BOPTEST. And I'm delighted to have with me today Parastoo Mohebi and Iago Cupeiro Figueroa, who are going to be giving two very complementary and related presentations, looking at both the theory and some of the practical implementation of this. So this webinar is presented and hosted by the IBIPSA Education Purpose. And the IBIPSA Education Committee exists in order to identify education and training needs throughout the building performance simulation community. And that includes everybody, whether you're academics, whether you're in the private sector, whether you're in the public sector, in government, and so on. And our aim is to initiate and encourage the development and coordinate new education material and methods. And we offer training sessions like this, really importantly, for free, and they're open to non-members as well as members. And we recently added a fourth item to our purpose, and that is to support and promote the development and sharing of best practices in building performance simulation education. So do look out for more about that new purpose as we move through this academic year. For now, though, I'd like to invite Parastoo and Iago to say hello. And I'm very lucky that I'm also joined by a very expert colleague, Esther, who is going to help me with some of the questions and answers. So welcome, guys. It's great to have you here. Thank you so much for joining. The way that this webinar works, we're going to ask Parastoo to give us her presentation in a second, and then we'll follow that immediately with Iago's presentation. All your questions, please do put them into the Q&A box, and then Esther and I will put those questions to the speakers at the end of the two presentations. But do keep them coming as they are speaking, and if there are any that are general questions for IBIPSA, I will do my best to reply to those in the Q&A as we go along. So for now, thank you very much, everybody, and I would like to hand over to Parastoo. If you'd like to share your screen, please.
Hi, Pamela. Thanks a lot. Can you see my screen?
Sorry, Parastoo, you're on mute.
Hello, everybody. Good time. I'm Parastoo Mohebi. I'm a PhD student at Hong Kong University of Science and Technology, and I'm grateful for the opportunity to present my research at this webinar. The topic of my presentation is comparing different parameter identification techniques for optimal control of building energy systems. This project is supervised by Professor Wang at HKUST. Give me a moment. Okay, as you know, buildings account for a high portion of carbon emissions. On average, it's about 30 to 40% of the carbon emissions of the world. And since we are in Hong Kong, specifically in Hong Kong, around 90% of electricity consumption is related to buildings, and 60% of carbon emissions are building related. This shows the importance, this shows that if we want to move forward and move toward the carbon neutrality, we need to optimize building energy systems, especially during their operational phase. In order to do this reach this goal, we need to have reliable building energy models. And after selecting the structure of the model, for example, data-driven black box models, semi-physical gray box models, or physics-based white box model, since we can interpret the thermal dynamics of the building with a gray box model, and they don't need to train lots of data. They are preferred for especially control purposes. And after selecting the order of the model, one of the important stages is parameter identification. And when we reached the parameters, the distribution of the identified parameters, an important step is to evaluate those parameters. There are different metrics for that. For example, prediction accuracy, the resulting energy cost and thermal comfort caused by this, and the other metrics that may be important. The conventional rule-based controllers have been used for controlling building energy systems and reducing the energy cost. But by growing complexity of the buildings, the growing complexity of the building energy systems, this kind of controllers are not so efficient anymore. And because of that, a promising approach that has been used is model predictive controllers. These are MPC is a technique to find the optimal control action at each time step, by predicting the disturbances ahead, disturbances of the future, and also considering the mathematical model and the comfort constraints that we have. And one of the important steps for MPC is parameter identification too. During our research, which is published recently in Energy and Buildings, we have considered these 3 steps of a model structure, parameter identification, and finally we have evaluated the identified parameters through different metrics. During our research, studying the literature, we reached 2 research gaps. The first gap was that we reached the lack of studies that comprehensively summarize various formulations and hyperparameters employed in the parameter identification task. And the second gap was that there was absence of research that evaluates the efficiency of various parameter identification models. In order to address these 2 gaps, we considered 3 objectives for our research. Firstly, we want to formulate the parameter identification task using different optimization models. After then we want to obtain the distribution of the parameters, and we want to evaluate the obtained parameters using different metrics. In order to reach this goal, firstly, we needed to have a building energy model. We considered a gray box resistor capacitor model that considers the effects of 4 parameters, including 4 disturbances, including solar radiation, ambient temperature, heat gain due to occupants, and the heat gain due to the HVAC system. By considering the concept of state space models, we can say that the indoor temperature of the building is our state variable here. And our goal is to find the distribution of 4 parameters: the thermal resistance of the building, the thermal capacity, the effect of the solar radiation, and the coefficient related to the effect of the heat gain due to occupants. And for our parameter identification, we have 2 different models. As you can see in both convex and non-convex models, the objective function is the same. It's to minimize the error, which is the difference between the between the ground truth data or the ground truth temperature and the model temperature. But the difference is in the constraints. As you can see, in the convex model, the temperature or the state variable is updated at each time step using the ground truth data at the previous time step. While in the non-convex model, the state variable at each time step is updated using the modeled temperature at the previous time step. If I want to summarize the difference between these 2 methods, we can say that the non-convex model is better in terms of data requirement because it needs less data. It doesn't need, it uses just an initial value for temperature and doesn't need the ground truth temperature of each time step. It's more similar to the MPC approach. On the other hand, the convex model guarantees to reach global optimal solutions and has less computational challenges. If it is important to share the overall view of the methodology, when we got the ground truth data using BOPTEST and the baseline of BOPTEST, we used them in our parameter identification task. And after we obtain the distribution of RC parameters, we evaluate them using different criteria. The first metric is temperature prediction accuracy, which has been investigated in lots of researches. The second metric is the the spread of identified parameters. This metric is important since in the absence of retrofitting, we expect that the thermal characteristics of the building be relatively unchanged and in a small range. And with changing the subset of the data that we use, we expect to reach similar thermal characteristics for the building. But the final metric, which is the focus of this research, is the effect of RC parameters on the MPC performance, including energy cost and also thermal comfort. Because the final goal of having an energy building model is to minimize the energy cost and increase the thermal comfort, maximize the thermal comfort as much as possible. So this metric is so important for evaluating the identified parameters. It is noteworthy to mention that during our methodology, we need a framework. Firstly, for getting the data, obtaining the required data for our optimization model, for our parameter identification model, and secondly, we need a framework to evaluate our MPC model in that framework and building framework. Here, we use BOPTEST to do these 2 tasks. In the BOPTEST, we use the BOPTEST hedronic heat pump test case, which is a single zone residential building in Belgium. This residential building works with a heat pump and the features that you can see in this slide. And this building is occupied by 5 occupants, and it has it's a special features, HVAC system, and these data are here. Now, let's move on to the results part. As I mentioned, the first metric that we wanted to evaluate was the prediction accuracy. As you can see here, in the figure and in the table, in both peak heating period and typical heating period, which are the BOPTEST weather condition scenarios, the non-convex model outperforms the convex model in terms of prediction accuracy. And when we increase the optimization horizon, as we expect, the prediction accuracy decreases. The second metric is the spread of the identified parameters. As you can see, the non-convex PI model exhibits higher standard deviation. The first two rows are related to the convex model. The second two rows are related to the non-convex model. As you can see in the third row, which is related to the non-convex model with a 24-hour optimization horizon, we have the largest variance of parameters. And the second result is that an increase in the optimization horizon leads to a decrease in the standard deviation. And here I want to emphasize the effect of our obtained parameters on the MPC performance. The gray area here is the feasible area for MPC results, because at least the MPC controller should work better than the baseline in terms of both thermal discomfort and energy cost. As you see in all the cases, the MPC is working better than the baseline, except for one case in typical heating scenario, which is related to the parameters obtained from non-convex model in the 24-hour optimization horizon, in which the thermal discomfort is about 2 times of the baseline. And since in our work, the overall performance of MPC is important for us, we want to consider the overall performance, including the weighted cost, including both thermal discomfort and energy cost. And as you can see in both weather condition scenarios, all the MPC controls are working better than baseline, except for that non-convex model in the 24-hour optimization horizon. And when we increase it, increase the optimization horizon, the non-convex model even works better than the baseline. And in both cases, the convex model with a 48-hour optimization horizon has the best performance. Now here, I want to present the significant part of this research. It was that when we optimized we run the MPC controller with different input data, including 12 weeks data, 3 months data, and 1 season data, we reached the result that when we increase the sample period or the amount of the quantity of the input data, it helps the controller to have better performance, and it reduces the risk of selecting an unsuitable period of time as the input data. And in this discussion part, I want to emphasize that we can interpret our results through the bias-variance trade-off. In the bias-variance trade-off, as you see, when the model is less complex, like the convex PI model, parameter identification model, we have lower variance and, on the other hand, higher bias. The lower variance is related to the global optimality, and the higher bias is because of the divergence of this model from the control task, because we are using the ground truth data at each time step for updating the next time step. And on the other hand, the non-convex model has more model complexity. It leads to higher variance and lower bias. The low bias is because this model aligns with the control task. We are predicting multiple time steps ahead, like the control task, but it leads to higher variance. The higher variance because the solutions are local optimal, and this method does not guarantee to reach the global optimal solutions. Here I want to summarize our presentation and mention two takeaways. The first one is that a more accurate model does not necessarily lead to a better control performance. Here, the non-convex parameter identification model leads to better, the non-convex parameter identification model leads to better prediction accuracy, while the convex one leads to better MPC performance and a spread of identified parameters. On the other hand, the second takeaway is that when we increase the data quantity, it improves the MPC performance. When we expand the sample period, it helps us to reach the better MPC efficiency, and it reduces the risk of selecting an unsuitable period of time. So we can suggest that since the final goal of this research is to minimize energy cost and maximize thermal comfort as much as possible, we can say that the convex parameter identification model and increasing the data quantity are suggested. And since in this presentation we used the average of the identified parameters for the MPC controller and we didn't use the total, the whole range of the identified parameters, there may be in the next project we consider to develop a chance constraint and stochastic framework to consider the whole range of parameters, that not just the average of them, which is the topic of our next project that we skip this part because of the time limit. That's all for my presentation, and thanks a lot for your attention.
Thank you very much, Parastoo. That's great. Iago, if you would like to share your screen, I would like to invite you to give your presentation. Anyone in the audience who has questions for Parastoo, please do pop them into the question and answer box, and we'll pick them up after the Iago's presentation as well. Okay, thank you, Iago. If you'd like to go ahead now.
Yes, just gonna put my timer and let's start. Hello, everybody. It's a pleasure to be here. My name is Cupeiro, and I'm well, right now I'm a freelancer. I did my PhD at KU Leuven a few years ago on MPC applied to geothermal systems. After that, I started working as an employee for Delta Q at the time. Now it's Energy, but after a small pause, I decided to work as a freelancer. But I still work for them most of the time. So next slide. Well, here what we are going to talk about is the new emulator that has been already published in BOPTEST, from which we have been working from the energy side. And the context here to start this work is that we have BOPTEST, amazing tool. You can select a test case for a set of test cases. Then you can do whatever you want with your test case. You can initialize, simulate for a period that you want, reinitialize again. You have customized periods, and most important, you have standardized KPIs that they are reported, and they allow you to compare your models with other people. So it opens the way to some sort of competition. But from January at the moment, we saw that none of the emulators was close to what we were seeing in real buildings here in January. So we just talked with the consortium and we decided to develop a new test case, Hydronic, that resembles more the typical topology that we can find in office buildings that we have encountered. So here's a small disclaimer. This information comes most from industry experience. Just we didn't do any kind of study or something to know what is the most common topology here. On top of that, we also wanted to develop this simulator that closely resembles the real hydronic office building, but also we wanted to have a trade-off between simplicity and fidelity in the building representation. Simplicity, because if we put a too complex emulator model, we could kind of scare the people and they will not like to use our model because it's too complex. So we wanted to make it a bit easy in that way, but also it needs to be fitted to what we found in real buildings. Okay, so let's get started with the model that we have developed. It's an office building that is located in Brussels. So you can expect like a European continental weather. It's a 5-floor building with 15-meter high and 50% window to wall ratio. And it's open between 7 a.m. and 7 p.m. So during those hours, you will have your occupancy that is provided. We divided the building in two spaces, two zones, one that's pointing towards the north, one that's pointing towards the south. And as producers, we use a heat pump and a chiller, and the end units or the emission systems, they are ventiloconvectors, or also called fan coil units. And in the documentation, you will get everything that you need from the building, like wall compositions, occupancy profiles, performance maps of the heat pumps, nominal powers. This is like a candy for you, I will say, because this is normally not what you encounter in real buildings. Normally, you encounter some data that many times is a bit corrupted, and then, well, you still have to work with that in industry and develop an MPC for that building. So that eases things a bit more. Let's get to the topology of the building. So each space, which is here, I hope you can see my mouse. There's the south space and the north space. It's has its own set of fan coil units and its own dedicated air handling unit, which simplifies the things. It allows you to even create an MPC for one of the spaces and let the other space with the baseline controller if you want to simplify things and go step by step. And you have the producers, the air source, heat pump, and the chiller. They go towards a collector, and each collector has a circuit that feeds either the fan coil units. Oops, sorry about that. It's the fan coil units or the coils in the air handling unit. So let's get a bit more in detail of what you control. What can you control actually? The blue symbolize like real control signals that you can control, and by real I mean you can vary between a range. In case of the air source heat pump, I think was between 20 degrees and 50 or 60 degrees, something like that. And well, the same for the chiller. The orange ones, they are binary variables. You can only write a 0 or a 1, so you cannot modulate this pump, and that's something that you encounter in buildings. Like many of the components, they are not modulating. So if you work with NLPs, nonlinear programming like me, then you have to deal with this with some sort of post-processing. But more of that will come later. So the producers feed a collector to have a certain temperature, and from here you have circuits that go to the fan coil unit coils or to the air handling unit coils. You can activate the circuit with the pump, the individual circuit with the pump, and you have a three-way valve, a mixing three-way valve that allows you to control the individual temperature for each circuit. And here you have two options. You can provide the set point that you want for your emission heat system or for your air handling unit, or you can control the actuator directly. So this is something that we encounter in buildings, like these three-way valves. You can actually control them, but you have to be careful because of the normally granularity of your time steps. If you have a time step in your MPC of 1 hour, that's gonna be a bit risky from experience. There is a baseline controller. The baseline controller will set the temperature here for the producers as the maximum or minimum demanded by the circuits, depending if it's for heating or for cooling. And these supply temperatures in the baseline controller, they are a heating curve for the fan coil units, and they are set to constant for the air handling unit coils. And the pumps here, they work on a schedule. They work from 6 a.m. till 7 a.m. Remember, occupancy starts at 7 a.m., but you want a bit of preconditioning on your space before the occupants get into the space. Except for Mondays that they start at 4 a.m. And for the air handling unit, they work from 7 to 7. Air handling unit just follow the occupancy schedule. You want to provide ventilation when there is occupancy. On the other part, well, we have here the air handling unit with the coils. And then you see here that you can control the supply temperature of the air handling unit. And by controlling the supply temperature, there are some internal controllers that they will modulate these valves to decide how much heat flow does it need to go through the heat exchangers. The same happens on the fan coil units, and these are not controllable. We normally find in buildings that when an end unit or emission system is connected to the BMS, you can only control the set point. You cannot access these actuators. They are not controlled to the BMS. So you have to deal with that and find the solution. You also can control the bypass of the recovery of the air handling unit if you want to provide some night ventilation and the fan speed. But in the baseline controller, this is set to full speed, following the schedule, and not that much to say about the air handling unit. And for the fan coil units, set points are set 21 for heating and 25 for cooling. Also during the when the circuit is on here. More things that I want to say about the controller. It's no, I think I said everything. So I'll just go for testing the methodology. So now we have developed our emulator. It's available for you to use. It can be scary at the beginning, but I ensure you that you will have fun with this emulator. And we decided to put it to test with some MPCs. So let's see what do we get. We selected the peak heat day period with electricity pricing constant, and we train an RC model of 2 states that has integrated HVAC. So the HVAC is modeled more in a white box way, and includes the valves and includes the heat exchangers and some parameters that you want to estimate also from this model. Not gonna get into detail into that because of confidentiality reasons. But this model, then we translate it using Casada into a nonlinear optimization problem. And what we control here is the supply temperature of this circuit. So basically temperature that goes here, the temperature of the air handling unit that we are supplying to the air handling unit, and whether we activate the circuit and the end units or not. But that's a bit cumbersome in the sense that we are using a nonlinear programming, so our variables will be between 0 and 1. So at the end, you need to post-process this part somehow. You have to deal with that when you work with NLPs. So in that sense, we tried 2 models, one that includes the PI into the model and can compute the set point directly, another that controls the valve opening. And then we have to post-process that valve opening into a set point here. So we choose 2 kind of post-processings here. One is that when the valve is open more than 5%, then we decide to open the circuit and to activate the end units, the emission system. And in the other, we set it to 20%. So when our valve is open more than 20%, then we activate the circuit and we put we activate the circuit and the end units. This is the results of the training. To be honest, this was the first go of the training, and for me, this was already a good enough model with RMSE of 0.3 and 0.44. For this testing was enough for me. We could improve the model by adding orientations to our solar input. I think that will greatly improve the model and avoid these delays. For training here, we were using the global horizontal radiation. And something that I like to look, I think in the previous presentation, we saw that more accurate model doesn't lead to better performance. We normally look at the RMSE, but something that I personally like to look is how is the steep when you activate the heating. So how feel is this? Like, for example, here, I don't like it that much. Here is more or less perfect in line, but when you have this sort of behavior, that can really affect you when you try to heat up your building for the morning. And then we have the results here. So we have the baseline in blue, MPCs with the valve opening at 5% with the PI, 20% with the PI in the model, and here by controlling directly the valve. We see that our best result was using the PI in the model, including the PI, and already activating the circuit when we spot that the valve is open 5%. So we see that compared to the baseline, our best MPC was able to reduce about 15% in the energy use. Well, this is the emission and the energy, which are the same in the constant scenario. The peak was also reduced. It was nice to have. I was not expecting to have this, to be honest. But we see that the discomfort increases a little bit, especially in the case of the valves with when you open more than 20%. And we are gonna see now why. We get more in details with the MPC with valve opening at 5%. By the way, these are the results, including the PI on the model here. And what we can see here is that most of the gains here come from reducing the temperature. We set a lower constraint on the supply temperature of 40 degrees, and this is what the MPC likes to use, which reduces the producer power, like the boiler power, which is in the third plot here. Also, something that is here, these are the temperatures of the two spaces, and we see that the baseline supplies at 21 degrees constant. Here, our MPC likes to supply at 20 degrees. That was the lower constraint, because it needs less heating to set the supply temperature at 20 degrees. Even if it's putting some cooling into the building, prefers to use this 20 degrees. And something that also gets some savings is just deactivating the circuits when we don't really need them here. We can see also here that the MPC can select two different preconditioning times. These lines here are the Funkwell unit powers. So, for example, in this case, the north zone started a bit later because it's designed to have more power since it's the north zone here. And these small here are the circuits. We just get some savings from turning off the circuits. And here the comfort, it changed from 4.8 to about, I think it was, if I remember correctly, was like 7. But if I see this solution in real industry, for me, this is a perfect valid solution. Even if you get a bit of discomfort in the morning, normally in the morning, in 7 a.m., the building is not that much occupied, and people normally walk into the office and they have their metabolism increase. We normally never get a comfort complaint because of this. If I get this result, for me, it will be totally valid for the industry. In the case of the 20% opening, then we have a problem here because we have some oscillations. And here, oscillations is what really concerns me from the industry point of view, because of wearing of the components and also the peak power that you need to start up your components. So here we see that the pumps, they are oscillating with this, of course, 20% opening. Here, the MPC doesn't reach the 20% opening, so the circuit is closed, temperature starts to decrease until the point you reach this 20%, you open it again, And this, for example, this will not concern me for discomfort either, because we are very close to the comfort bound. In comfort terms, where you can get most of the complaints, I will say, is if you are like at 25 and suddenly you go at 20, occupants really feel that, to be honest. But these things, if comfort-wise, they do not concern me that much. But in terms of energy use, this is, even though that we decrease the energy use, I will be concerned about this. But okay, we could see that even with the non-perfect model, we managed to get some savings in this BOPTEST emulator. Here, the conclusion is that we have a new building emulator for you that has been added to BOPTEST. For us personally, for me personally, this emulator helped me to evaluate different post-process strategies of the NLP. They are really important when you work with nonlinear optimization, transform the value, the variables that they are binaries, because you will get a non-binary variable, and you have to be, you can get really huge savings if you do it properly here. So for us in the future work, it will be evaluating more scenarios and of course make conclusions on what kind of post-processing is more beneficial. Improving our PI model seems like is the way we have to go, and this is thanks to BOPTEST, because we have just checked out that the PI model was better in this case than controlling the actuator directly. Just for the reason that we cannot control the actuator directly, we have to transform it into a set point, and that post-processing is just harming us. And then a few final remarks that I have for everybody. Just know that real buildings get complex, much more complex than this emulator, really. It's you can have, instead of one air handling unit to one space, can go to 2 spaces, or one space with 3 air handling units, and you have to space it like that because there is only one circuit going to that space. I mean, you can get much more complex, but I would say don't be afraid, embrace this complexity, test your controllers, please, in these complex cases. I think it's totally worth it for the industry. You also have to cope with uncertainty, like we have cases with controllers that go offline, buildings that they are not responding to your commands, these little things of the real world. Latencies, that's the time that you have between you compute your MPC until you put it into the building. Also, occupancy behavior, they can open doors, windows, your model cannot predict that, but it has to be robust to cope with that. But in essence, what I want to say is just challenge your controllers with a difficult test case. I think there is real value in this. And exploit the flaws of the building. Buildings in the real world, they have flaws, they always have flaws. And sometimes big gains just can come from a simple RBC. Like I have seen buildings where the air handling unit is on 24/7, and just by putting a schedule on the air handling unit, simple RBC, you get big savings. And for us, it's more important to have a bit of savings in the whole portfolio of buildings than a lot of savings in just 2 or 3 buildings. So don't be discouraged by this. Remember your mission. We're here to reduce the CO2 of buildings. And of course, we look forward to seeing the results of the community. Just the last slide for my funding, especially here on the left. And with this, I conclude my presentation.
Thank you, Iago. That was great. Some really impressive savings there as well. Quite striking. I'd like to invite Esther and Parastoo to join us as well. And perhaps you could stop sharing your screen, Iago, for now. We already have a few questions in the chat, but just before we get to them, I wonder, Esther, if you would like to just say a little bit more about BOPTEST and the sort of the broader project and how these projects that we've heard about just now are linked into that.
Thank you a lot, Pamela. Yeah, so what we have seen now, one of my key takeaways from these 2 presentations is that the choice of emulators is, of course, very important. And Iago, you have handled the emulator issue by just developing a new one because you couldn't find one that was suitable for your problem. And Parastoo, you've just selected an available emulator that was already there, which is for a heating scenario. And I was just wondering, because you are based in Hong Kong, which is, I guess, a more cooling dominated country, a region. Have you thought about how your results would change if you would have selected an emulator in a cooling dominated country?
Actually, do you have my voice? Yes.
Yes.
Okay. Actually, during this research, we wanted to test if the performance or the evaluation of different parameter identification methods. And these parameters may be, yes, related to the location and the weather condition. And if we want to consider them for a place like like Hong Kong, we need to have a test case that considers the cooling demand, and maybe these parameters would be different, but the methodology, the overall methodology can be implemented for every location.
Thank you.
You're welcome.
That's great. I'm going to move to the questions from the chat because we've got lots now, which is fantastic. Do keep them coming. The first question is for you, Parastoo. So thank you very much for the nice presentation. And the question is, the question is wondering about the difference in computational cost between the methods, and is the convex parameter estimation approach significantly cheaper than the non-convex?
The convex, let me share my screen. Here. The issue is that when we use the convex parameter identification, we reach the results that guaranteed that we will stay in the feasible region for the MPC. It's a guarantee to have better performance than baseline. But the non-convex model, since the solutions are not essentially global optimal, maybe we reach, if we have a short horizon optimization, we may reach solutions that are not doesn't make MPC work better than the baseline. But if we increase the optimization horizon, it helps to exclude the extreme conditions, the extreme points, and the solutions will be better and will work in the feasible region. The problem is not just the cost. Maybe if we use the non-convex parameter identification model in a short horizon, maybe the resulting controller doesn't work better than baseline.
Thank you. That's quite a compelling case. And while you're sharing your screen, could I ask you just to go back a few slides? We have a question from somebody in the audience who's asking if you could explain a bit more on this slide, I think, the difference between these two solutions. They're asking if you could elaborate why the first formulation is convex and the second is non-convex.
Okay, in our optimization model, the optimization variables are parameters of the model, which are A and B here, A, B, C, and D here. And as you can see in this optimization models, we want to find, we want to find these parameters. And here in the non-convex model, as you see, the state variable is also a variable, and the multiplication of them makes that this equation is not affine. It's not an affine transformation, because if we write this equation, all of them will be related to the initial point. It's not an affine transformation or constraint, and because two variables are multiplied together, this makes this model non-convex.
Thank you. That was really clear. That's really helpful. Thank you. And another question for you, which is, in fact, two questions. So, what future disturbances are considered in the MPC? For example, do you include the weather forecast in that? And then the second is about the achieved cost savings through implementation of the MPC. Is that due to decreases in energy demand, or is it due to shifting demand to lower price periods?
Okay. About the first part of the question, we considered the weather disturbances. We considered the effect of solar radiation, ambient temperature, and for the internal effects, the heat gain due to occupants and heat gain of the HVAC. So yes, we predict the future weather condition and we use them in the MPC framework.
And in relation to
about
the cost savings, is that due to an overall decrease in demand, or is it due to shifting demand to lower price periods?
Okay, we don't change the demand here. We don't change the demand. We are just trying to control indoor temperature in a condition that we still be in the suitable region. Let me show you this appendix slide. As you can see in the first figure, we are still in the feasible region, in the comfort range for the occupants. So we are not decreasing the energy demand. We are just controlling the demand. So for example, here, you see the black line is the MPC results. Here, that for example, this building is empty in this time step, in this period. It's the weekend. And this period, for example, the building is empty, and because of that, because there is no occupant, the range of the comfort is higher. It can be between 15 degrees to 30 degrees. And here, as much as possible, we are trying to have less temperature, lower temperature, so we use less energy. But that doesn't mean that we are sacrificing the comfort of the occupants. We are paying attention to both of them at the same time. We are just controlling the indoor temperature, and while at the same time we want to stay in the thermal in the comfort region for the occupants.
Thank you. That was very clear. Thanks very much. So the next question, I think, is for you, Iago, which is, again, thanking you for the great presentation and all the work on the BOPTEST emulator, and asking, as an expert from industry, what do you think the most relevant topic that academics should investigate to bring value to real-life problems? There's quite a philosophical one for you there.
Many things, actually. Think about many things, but you have to, like when I was working or studying at Cupeiro at PhD, most of the papers that I used to read, they consider a lot of ideal conditions, like we have perfect predictions and we have these sensors are available and we have these measurements of the heat flow, but then you get to real industry. Half of the measurements are wrong or biased. They are not working. You don't have the technical sheets of the building. They are lost, so you cannot see how the building was built. You don't have any information on nominal powers. So actually, for me, it's just challenge your model with difficulties, make it more robust, because this is what you're gonna encounter, like, for sure.
Thank you. I think that's great. It's very much the case that
Yes.
some of the savings, the biggest chunks of savings, can just come from buildings needing to operate how they were intended to, rather than what's actually being done at the moment. And that lack of knowledge of what and lack of appreciation sometimes within academia of just how complex the real world is
Yeah,
can sometimes be an issue.
there is also a lot of friction, like because in a building you have several parties. You have the tenants, but you have the building owner. Normally they have conflicting interests. There is normally an operations guy on the building, but the operations guy sometimes thinks we're gonna steal his job, and that's not the case. We want to help him to do his job better, but he normally doesn't look it that way. So it's a bit of friction, and they normally don't like the building owner and the operations manager. They just care about the comfort, because at the end
Yeah.
of the day, it's the tenant who's gonna pay the bill. But then I just remember one operations guy who wanted to keep everything on 24/7 just because he didn't want to get any comfort complaint, and that's a disaster at the end because it's so much energy use. But just because they are scared, they don't want to even try, and you have some work on convincing them. It's painful sometimes, but we
Yeah.
have to remember why we are here.
Absolutely. And if people are interested in that topic in more detail, I would recommend you have a look at some of the previous series recordings that we did, looking at human-centered approaches to design in buildings, and that's all available on our YouTube channel, and I'll show you the link for that in just a second. But just before I get to that, I'd like to just ask Parastoo one final question from the audience, which is about whether there's a reason for not considering thermal heat loss due to air exfiltration from the building's bases to the ambient environment in the thermal calculation formula, or is that a limitation of the work?
Sorry, could you repeat the question? I
Yeah.
didn't quite get.
So the question is asking if there is a reason that thermal heat loss due to air exfiltration is not included in the thermal calculation formula.
Okay, here we have used RC model, which fits the best with our obtained data from BOPTEST. We tested 3R2C model, but we reached a much higher error in predicting the indoor temperature. So this RC resistor capacitor model fitted the best with the data, and it reached to the least error, temperature error.
Great, thank you very much. Now, I said this was the first in a new series of webinars, and because of that, we would like to ask you some questions about this webinar that will help us with the planning for the future webinars. So there's 6 questions here, and I wonder if you would mind. I've just launched the poll there, and if you could let us know what you think, that would be great. I won't run through the questions in the webinar just now, but do please use the poll button that should have popped up and give us your thoughts on these. I can see that quite a few of you have participated already, so that's brilliant. That's really helpful for us. So while you're doing that, I'm just going to share my screen again and tell you a little bit more about where you can find the recording, both for the previous series and also for this webinar shortly after this session. So we have a YouTube channel which has the recordings for all the webinars that we have hosted in the past. So this is now our 6th series. We have a huge archive there of really valuable content. A whole education, really from beginning to end in building performance simulation, but also in some quite specialist aspects of it. We've had a lot on urban building energy modelling, for example, and there's lots more coming too. So do like and subscribe to that channel to be informed as new content is released, and make sure you join us at IBIPSA. You can sign up to the mailing list on the website so that you can be kept informed of future sessions. And you can also consider joining us as a supporting member. So the supporting members provide an income for IBIPSA, which is incredibly valuable in supporting IBIPSA's work. And in return, they receive a subscription to the Journal of Building Performance Simulation. You can either have a print subscription or you can have an online-only subscription. And you have the right to use the IBIPSA supporting members logo. The prices are remarkably fair, having remained unchanged now, I think, for almost 5 years. And as we approach the festive season, perhaps this is the ideal gift for that special someone in your life who's interested in building performance simulation. But with that, I think we've just hit the hour, so I'd just like to say thank you so much to everybody on the panel, to Parastoo, to Iago and to Esther for a really illuminating insight. And thank you so much to all of you for joining us. It's been great. Do keep in touch on LinkedIn, and I look forward to seeing you again soon. Thank you.
Thanks a lot. Goodbye.
Thank you, everybody.
Thank you, everyone.
Thank you, everyone. Bye-bye.